Okay, I think we are getting slowly ready to start today's QuTech360. So pleased to welcome all of you. And also online, we have some people that's great to see. So that's good. Today's speaker is Francisco Machado, who is a group leader at QuTech in the Quantum Internet Division, one of our newest PIs in QuTech. So that's great. Uh, Francisco did his bachelor at MIT and did a PhD at UC Berkeley. And following that, he was a ITAMP postdoctoral fellow at Harvard, where he worked on quantum information, quantum sensing, and many-body physics. And now in the Quantum Internet Division, he will continue in this triangle along those three axes. And I'm sure he will tell you more about that today. Please make sure to ask questions during the talk if you are interested, and also online if you have questions, write in chat, and we will make sure to see it. So with that, please welcome Francisco.
Perfect. Yeah. So I have kind of this view that in many ways, one of the cool things of that we're doing here at QuTech and we kind of want to push is trying how do we understand how we can develop quantum technologies, find new applications, actually build a lot of the kind of the new wave of technology. And the thing that I like, that I think when I think about this is that technology development is both fast and slow. So this is kind of some data from the world of data, for example, of adoption rates of different technologies. And what you see is that there's this very steep S-curve where basically there's very little adoption of technologies, whether it's like the radio, the automobile, the cellular phone. And suddenly there's a massive adoption, and then it kind of like flatlines because you cannot sell more iPhones once everyone has an iPhone. But the interesting thing is like this feels like a very fast on-ramp and feels like things are changing very fast. But when you think of like the key conceptual, the fundamental laws of physics that kind of that gave us this kind of these kind of advances, they actually came much, much before. So when you think of, for example, Maxwell's equations, it took us about 70 years to actually propagate into like having a working radio and putting a radio in every household. The same of like the auto cycle and kind of the automobile revolution. And when we think of the band theory of solids and kind of the microcontroller explosion, there was also a big gap. And this is what I mean by it being fast and being slow. Even though we might have known the rules that kind of like underpin the phenomena that we're going to build a technology, it takes a while to develop the know-how, to identify what we need to build, and actually to have those things propagate through society. And indeed, in many ways, kind of, if we kind of think in timelines and we kind of do a little bit of numerology, quantum mechanics kind of on that trajectory. If we think of, we recently celebrated 100 years of quantum mechanics with the introduction of the Schrödinger equation in 1925. And now we're seeing exactly the onset of the ability to control quantum mechanics and actually propagate it. But the fact that it's kind of like, seems like it's a slow evolution, even though it's been speeding up so much, is that it's a hard technology to solve. There's a lot of like hard things that I don't truly know about. For example, cryogenics, there's a lot of manufacturing. But there's also an application perspective, which is like, even if we were to build a quantum computer tomorrow, where would we use it for? What are the key applications that would give it widespread accessibility? And then there's also this question of infrastructure. For example, in the context of the internet division, even if I today build the best quantum internet node, I would have no one else to communicate with. So once again, there's kind of like these things that we need to address. There are theoretical and kind of like conceptual problems that we still need to solve, but are important to actually get the technologies to build up. And I think that this is kind of like very noticeable, for example, when we think of also in the context of quantum computing. For example, when we think of the technical capabilities that we have today, we think of, for example, 2-qubit errors on the level of like 1 part in 1,000. But if we want if we actually want to run algorithms, what we need is a 2-qubit error on the level of like 1 part in 10 to the 10. And when you think of today's kind of applications that we run these quantum machines for, it's a lot of proof of principle demonstrations, kind of small scale understanding what these machines are for, how we can kind of build understanding. But the useful applications are kind of very, very far out. They're kind of these promises of, for example, breaking RSAs. You might have seen recent papers about, but also, for example, quantum simulation. And indeed, there's a large gap to overcome, and that's kind of one of the challenges that brings all of us together here. But there's kind of in some sense, an easy thing that we need to solve. For example, this error part. We know that error correction, we're going to get there not necessarily by building machines that are 7 orders of magnitude better, but by actually using error correction to suppress errors and allow us to do this logical, have those levels of error rates on the logical level. But for me, what's kind of interesting and kind of less obvious is how exactly do we expand and how do we kind of build a zoo and kind of a zoo of application and a zoo of technologies such that when we actually build the machines that reach 10 to the minus 10 error, we then can actually use them to kind of use them widespread in society. Okay. And the way that I kind of see it is indeed we can try to take this bridge. We have a very challenging gap that we need to overcome. And there are people who are working very hard on that in trying to make that jump. But the thing I like, and I kind of been building my research about, is actually trying to sidestep this problem. And not necessarily go directly into tackling this one, but trying to explore the broader landscape and try to find different routes that give us new sets of applications, new opportunities, and understanding what we need to build that gives us kind of different applications for quantum. And there, that kind of like falls within 3 buckets. One is quantum sensing, the other is quantum simulation, and the other is more very connected with the quantum internet division, is understanding what kind of novel quantum architectures we can build and what kind of insights they give us. So let me kind of like flesh out these questions a little bit more. So in quantum sensing, I think the key question we want to answer is exactly how does quantum mechanics enable us to sense in a fundamentally different or better way? The second of quantum simulation is how can we use the ability of shaping nature's rules that these machines afford us to actually study materials and emergent phenomena that don't emerge on classical systems. And finally, in the realm of these novel quantum architectures, the question is how exactly can we interface these quantum devices with each other, but also with the outside world? And although I can I always like putting things on a spectrum. And so here, even though kind of there are three directions, I do see them as kind of like interfacing fields where if we develop, well, the point's not working super well. If we develop new ways of kind of performing quantum sensing that helps us in investigating emergent phenomena, insights that we get from emergent phenomena propagate into the way that we know how to correct errors, and the way that we can build, for example, networks of quantum machines properly will enable us new ways of sensing and sensing different kinds of phenomena. So today I want to do the impossible task of trying to give you examples of the kind of research I like doing around these questions in 3 different stories. And each of them hopefully takes about 10 minutes. But what I want to maybe motivate you all is to stop and ask questions. It's better if we only talk about 2, but what I talk is clear. So please feel free to interrupt me. I would actually welcome it. And so in quantum sensing, what I want to tell you a little bit is some recent work where we kind of demonstrated that if you take a quantum sensor and you kind of append it to a quantum computer, you can actually sense in fundamentally different ways, and you can sense fundamentally faster. And this gives us something that builds upon the Heisenberg limit advantage that we're used to learning in quantum sensing to give us a new kind of sensing advantage. The second I want to talk to you is about quantum simulation and how we can use the natural ingredients on these quantum devices to actually help us stabilize, prepare, and study topological phases of matter that are really challenging to see in the solid state. And finally, I want to tell you how, when we think deeply about how these architectures work, we can actually design much more efficient fault-tolerant delegated computation that preserve security. And this is what is known as blind quantum computing. And kind of the kind of through line that's going to go through all of these examples is that I truly believe that the theory and experiments go hand in hand. Whatever we learn from theory drives the way that we think of what experiment we should build, what experiment we should run. But as a theorist, what I find interesting is when experiments kind of like sharpen the questions that we should ask. They tell us what are the real constraints that we should consider, and they kind of guide us to ask the right questions. So with that, I want to start with talking a little bit of quantum computing and end sensing. So this is a good time for questions. Going once, going twice. Okay. So you might have heard of quantum sensing. It's usually seen as kind of a big application of quantum mechanics. And the way that I like thinking about it is that there's two ways that quantum sensing gives us a source of advantage. One is that it offers a new way to sense. And this kind of takes a fuzzy picture on which it can derive from the fact that we can just have better control over the physical system. There's the fact that we can now control single particles. So in some aspects, we can just get higher sensitivity or peak sensitivity in many ways. And the third is that we can just develop new sensing modalities that use the rules of quantum mechanics to sense in ways that don't really make sense in a classical system. For example, matter wave interferometry. And the fact that we know that this is a formative advantage because a lot of experiments now use this to actually get to the state of the art in sensing. For example, when people are measuring fundamental constants, or when they're measuring magnetic materials at high pressures, they use like quantum sensors, or even in our definitions of time, we use energy levels on single atoms as a sensor of time. But the thing I want to focus is how quantum mechanics actually gives us fundamentally better ways to sense. And that is a sharper distinction on which we can actually use quantum correlations or use the ability to process quantum information to fundamentally improve sensitivity in something that in a way that is impossible classically. And this is, as you might have heard, the distinction between the standard quantum limit, where the sensitivity of your system goes as 1 over square root n, where n is the number of sensors, to the Heisenberg limit, where your sensitivity can be improved to 1 over n. And this is indeed not exactly this scaling, but these ideas are exactly what LIGO uses to measure gravitational waves. So they don't necessarily get all the way to 1 over n, but they actually use squeezed states of light to boost their sensitivity. And what they see is that, let me see if this, no, this does work better. What they see is that if they didn't have this the squeezing, they would have a sensitivity like this. But by squeezing the light that they impart on their interferometry, they actually have a much better sensitivity that allows them to basically see a much bigger volume of the universe and search for black holes. So what exactly is quantum sensing? Yeah, thank you for the layup. So indeed, I think that that's a very good question that I want to clarify because it's going to be an important distinction I make in the talk. There's kind of different ways that you can think of quantum sensing. And often what I would say is that people think of sensing as a parameter estimation. So you have a magnetic field in your lab and you want to measure the magnetic field up to some uncertainty. And you might have some finite time, you have some finite amount of sensors. And the question is, how well can you do this task? And what the standard quantum limit tells you is that your uncertainty, if you have a fixed time, the uncertainty on this magnetic field scales inversely square root with the number of sensors that you have. And intuition of this is very simple. You have more sensors, so you have more information, but you also have more noise, and so you don't reap the benefit of all the sensors. The Heisenberg limit tells you that by reshaping the noise across those sensors, you can actually ensure that you can gain more information from having more sensors without actually increasing the amount of noise that affects your sensitivity. And that is why you have the square root. So answering your question directly, here I'm thinking of sensing as there being a classical quantity that I'm trying to estimate to some precision. But the interesting thing about this limit is that it actually doesn't care about the ability to process quantum information. So indeed, you can do this by just preparing a complicated state and then measuring it appropriately. So it's all about how we treat the uncertainty, like Heisenberg's uncertainty, and how we shape it, rather than actually how we can process quantum information. But the point that I want to make is that sensing can be different. Sensing is effectively how we ask things about the world. We can ask other kinds of questions. For example, is there a photon in my box? And that's more of a yes or no question. It's not so much of a quantity that I want to get some sensitivity. Yeah, so the way to think about this is if you think of a quantum oscillator, you have that the total x and p uncertainty is h bar. But that only tells you the total area of the uncertainty, doesn't tell you the shape. So if I want to get a better measure of x, what I can do is I can squeeze it in one direction and lose uncertainty in the p direction and actually reduce my noise in the x momentum. So if my coupling, my sensing is a measurement of x, and then I try to measure the position, I have much less noise, and I can use that to boost my sensitivity. Yes, so, oh, yeah. So the question was, why exactly, where is the trade-off? It seems like we're winning things. And so in the magnetic field, you should imagine that you have n spins, and you can imagine a Bloch sphere, a enhanced Bloch sphere of those n spin particles. And if you just prepare everything pointing along x, your uncertainty is going to be a big blob on the Bloch sphere. And here, what you can do, and basically what Heisenberg limit does, is you basically squeeze that uncertainty along, for example, the x direction, and you lose it in the z direction. So I don't have, so yeah, so you have your Bloch sphere that's like has a size of n. And if you pair everything along the plus state, you have some uncertainty that looks like this. And this is, let's say, the y direction, and this is the z direction. So this is everything pointing up, this is everything pointing down, this is everything pointing in the x direction, right? So what you can do is you can take this uncertainty and you can basically move it this way. And you can preserve the area while reducing the uncertainty in the y direction. Now, if you're sensing a magnetic field, this is going to persist sideways, but because your noise in that direction is reduced, you can improve your sensitivity and measure much more efficiently. If you're trying to measure magnetic fields along the other direction, you've made your problem much worse. So there's no free lunch. You need to know how to shape the correlations to measure the thing that you want to measure. Exactly. But indeed, like this is not the only thing we can measure. There's like other sensing tests we can ask. For example, is there a particle in a box? Is the frequency of my oscillating magnetic field in some particular bandwidth? What is the amount of, does the power spectrum of whatever device I have within some bandwidth exceed some value? And there are also sensing questions because they tell us something about the nature, but they're not, you can think of them as parameter estimation. And if you have a very good enough parameter estimator, you can solve these questions. But these are different kinds of questions that in principle you could solve more directly. And the thing that we were motivated by this, the question we were asking is like, can we do better by doing things differently and moving a little bit away from this parameter estimation and trying to understand different sensing problems. And so we kind of were studying a particular problem that we call the broadband AC sensing, which is very simple. So I give you a big frequency range. And I ask, is there an oscillating magnetic field whose strength is greater than some V min? The picture that you should have in mind is you have a telescope and you're pointing it at the sky and you're trying to look for some unknown particle, but you don't know the mass of that particle, but you just know that it exists. And you don't know, there's a lot of it that you don't know. So this delta omega can be very large and you're looking for a very faint signal. And you're trying to see exactly if the oscillating magnetic field there, for example, it might be over here or it might be over here. Regardless, I just want the yes or no answer to this question. And indeed, this is something that is motivated by, for example, axions and like searches for dark matter. Turns out they don't know where the dark matter is by many orders of magnitude. And if you can solve this problem more efficiently, you could maybe speed up how we can see or kind of detect dark matter. But even in more down to earth things, for example, when you think of high precision NMR, indeed, you're actually just trying to find a particular peak and you're trying to just detect the presence or not of some atom or nucleus. And the reason why this is an interesting problem is it kind of combines two ways that we know quantum gives us an advantage. There's the sensing problem that we want the B-min to be as small as possible. We want to sense very faint signals. But there's also the search problem, which we have this large bandwidth, and you're trying to find a needle in a haystack. You just don't know exactly where it is. And this has the problem, this has the same structure of search, and that's why this kind of combines these two aspects into one. So how exactly would you solve this? Now, the way that you probably do, if you have a AWG controlling your quantum sensor, is that you basically run some sort of CPMG-like sequence, where you kind of time your pi pulses in a way that you have some response centered at some frequency. And the width of that, how sensitive you are, depends on how long you run this sequence. And the sensitivity also depends on how long you run this sequence. So the longer you run, the more sensitive you are, but the narrower the frequency you're addressing. And then you basically do it multiple times. You do it for omega 1, and you get a little frequency bin. You do omega 2, you get a different frequency bin, and so forth and so forth. And if you run this protocol, you have kind of what I'll call a standard quantum sensing time that scales with how many times you run the experiment, which is this first parameter. And then the second parameter counts how many bins there are given your bandwidth sensitivity. However, if you have, instead of a classical control of a quantum sensor, you have quantum control of a quantum sensor, in principle, you can sense in superposition. And what I mean by this is kind of confusing. So what I want to say is, for each of the bins that we identified before, you should think that the quantum computer has a register. So there's a state on the quantum computer, 1, 2, 3, all the way to n. And you associate with a particular frequency bin. And then in principle, you can sense in superposition such that if you do a controlled CPMG sequence on the quantum sensor, you can actually sense the presence of the field conditional on the state of the quantum computer. Okay. Now, I'm gonna now skip this because I want to talk about other stuff throughout the talk. But in principle, you can actually do this in a robust way. And you can do it in a robust way such that your sensing operation is a very simple very simple thing. You prepare your sensor in the 0 state, you let it interact with your quantum computer, and what happens is that your quantum computer is going to pick up a phase of -1 if and only if there's a signal on that particular bin. And otherwise, the sensor is left intact. So I'm not explaining this. You have to trust me. And if you don't trust me, come and talk to me afterwards, and I can hopefully convince you. But the interesting thing about this structure is that you might have seen this object before, because this is what is known as a Grover oracle when you're trying to discuss how to solve a search problem. So we have a box that when we use it on our quantum computer, it puts a minus phase exactly on the element that we're trying to search. And because that's a Grover oracle, we can actually build a Grover search, which includes some sensing part interspaced with some Grover diffusion. And that gives us a very simple way of basically measuring out whether or not there is a signal or not. And together, because we have the square root enhancement from the Grover algorithm, we have a sensing time that goes basically the time it takes to run one of these Grover, which is about the same as before. But instead of a linear term, we now have a quadratic square root term on the number of bins. And that gives us a new form of advantage. And the key insight here is that we have provable lower bounds. We can show that in the generic sense where you have a quantum computer connected to a quantum sensor, the time it takes you to solve this problem has to scale like this. And the construction I told you before, if you go through all the details, saturates this bound up to polylogarithmic factors. And crucially, if you don't have access to a quantum computer and a quantum sensor, you basically are forced to take a time that scales linearly with this second factor, which in the limit of large bandwidths will always take longer. And so you can imagine that if I fix the amount of time that I have, for example, I have a PhD's worth of time to try to find the axion, what you find is that there's a much wider spread of parameter space that you can probe. If you're trying to aim for a particular B-min, you can basically reach a much larger bandwidth and kind of either find it or kind of discard that area parameter space. So the other key insight I want to convey is that this is kind of funky, right? Because when you learn quantum mechanics and when you've done the Grover oracle, the things you probably have learned is that you shouldn't use Grover's algorithm as a way of proving advantage, even though it does. And the reason is that if you did know how to implement the oracle itself on your quantum computer, you often know exactly what is the element you're trying to find. So there's this black box nature of Grover's algorithm that somehow we seem to have evaded. And the reason we have evaded is that although I can draw you exactly the circuit that needs to be implemented between the quantum computer and the sensor, we always need this additional element from the way that nature interfaces with our quantum sensor to actually implement the oracle. This is why the way that we like thinking about this as like nature as an oracle is the fact that we don't have knowledge about nature that allows us to kind of leverage this form of advantage. And the other insight I want to emphasize is this idea of digitization, which is kind of like I kind of glossed over a little bit about this, but in general, if you build a quantum sensor, its response is going to depend on the strength of your field and the phase and a lot of the details of the frequency, but we want this to be robust. So we actually want, and we can actually show that our construction gives us a robust yes or no question, provided that the field is above some particular threshold. And this digitization is very important because it allows us to robustly transduce the information from the sensor into the computer. You should think of this as an analog to digital converter. And now that you put your information in a digital manner, the quantum computer much more easily can process it. And indeed, you can kind of make this a little bit more precise and that you need this kind of structure. If you're trying to solve this problem kind of in a linear fashion, in a parameter estimation kind of way, by maximizing the QFI across the entire bandwidth, we can show that your protocol will scale worse. It will take more time. And this kind of tells you that you cannot solve these new sensing ideas perturbatively just by parameter estimating your way out of the problem. There's actually a different kind of design space that we should think about and kind of ponder, and those are places where you can actually get advantages. And the other thing that I think is important is that it also tells us that there's power to abstracting the properties of the signal. If we have this kind of analog to digital converter, indeed we can draw a picture where we have a sensor that we can kind of connect via quantum USB to a quantum computer, and then think of exactly how to run the protocol for doing the processing in a meaningful way. And so the thing that I want to emphasize with this is indeed this idea of like understanding, first of all, what is an interesting question, and then taking a step back of understanding what is the language, what are the problems that are worth solving and addressing. And indeed, this kind of opens an entire new set of questions for if it works for this kind of problem, what other problems can we actually design and devise new kind of quantum sensing strategies that go beyond the use of a quantum sensor, but actually we can use a little bit of computation to actually get higher improvements. And so this is kind of like the vignette number 1 that I wanted to talk to you today.
Yeah, is there here in this case with this quantum computation advantage a trade-off that is hidden and that you can like need to be careful of, let's say?
The reasons no and yes. So let me kind of unpack that. So it's no because we're not getting a free lunch. We're taking a quantum sensor and we're adding new capabilities, which is the ability to like process quantum information. And so in that sense, we're kind of adding elements, and that allows us to do more. So that's the way that we evade the no free lunch kind of intuition. On the practical side, what you do need is the ability of processing quantum information next to a quantum sensor. So the techniques that you have, for example, in the solid state, where you can just have like 10 to the 6 or sensors in a little bit piece of diamond, kind of go away a little bit out of the door, because you need to be able to process the quantum information. So then that's kind of like the drawback that you have. So I think that's kind of like why I think it's important to actually think carefully about how this can actually be implemented in experiments, because lowering that barrier is what takes to make this kind of like useful.
How easy is it to make this sort of oracle in general? Like, is it, I don't know, a simple task? Like, for example, if I want to measure any sort of, I don't know, crazy quantity, right? So do I really have to think hard about that oracle, or it just comes natural and then, okay, we have this sort of recipe that you presented here?
In the context of these oscillating fields, we have a kind of a prescription for making them, and we know exactly how it works, and we have a worst case scenario for showing that the error is bounded. I think an interesting question there is like, as you say, like, okay, now if we actually include limitations, how does it scale? But also we have a worst case scenario, so it might be that our suggestion is even better than we imagine it to be. But maybe the question that you're asking is like, the oracle is built for the particular problem of sensing these oscillating magnetic fields. I think an open question is like, for a generic question, how do I build the oracle? And I think more deeply, what is the oracle and what is the problem you're trying to solve? Because that's going to inform you how you actually take the quantum sensor and how you kind of digitize it and how you then process it.
For this particular, was this magnetic field sensing an example, or did you have a particular application in mind, like sensing some tiny electromagnetic dipole moments, or?
So I didn't go through it, but we kind of built a proof of principle thinking of like, for example, Tim's experiment, and assuming that you can do additional pi pulses to kind of like deal with some of the decoherence rates. But in general, I think that this could be mostly applicable in settings where you have very little knowledge of the bandwidth. So things like searches, where your signal might not be too small, but you just have to search for so much of like frequency space that in principle it would take a lot. And then there's where you have the win. It's not necessarily at measuring ultra small, because at the ultra small limit, your bandwidth is going to connect at the same point. So the biggest win is exactly when you move to signals that are not necessarily very small, but you rather not necessarily measure them sequentially, you rather measure them in parallel.
Okay. Did you have estimates for the sort of advantages you would get compared to some other protocol, and would it be for this like dark matter protocol? I was just curious about some example numbers.
We don't, and the reason is the sensing schemes tend to differ a lot, and goes back to this question about one way that they boost their sensitivity is by having a lot of sensors. So if you think a lot of these, they're, for example, spin-based dark matter searches, where they have massive amounts of diamond and they just like try to measure a little shift. Here is more amenable to LIGO, where you should think it's really expensive to build one machine. And so you actually benefit from trying to build a small processor on the side rather than build like another LIGO. I saw some other hands up.
Test? No, it works. The Grover kind of advantage is often lost if you realize it in practice because of the preparations of the states and finite coherence times and all that. Is this not a problem here? So what are the kind of the assumption on the quantum computer you actually need in order to get in this?
It turns out that even if you have finite T2, you can still win. But you need to think of where in this phase diagram you win. So you're not going to win on this corner. And the reason you're not going to win on this corner is because you're going to be limited by your decoherence rate. And so the reason you start winning the moment you can do a little bit of Grover. So you need to be able to do that Grover search element coherently at least a few times. But the moment you hit those, as you increase your B min, it means that you can actually squeeze more Grover cycles within your coherence time. So if you fix T2, the curve is going to look like this, and then you still get an improvement. So you still win, but then you need to go to very large bandwidths and very large signals so that you can kind of overcome this T2. But we're robust to the presence of that T2.
Maybe in the interest of time to also cover topic 2, which is 10 minutes, we could maybe move on.
Yes. So this was kind of like very much motivated by how can we sense better and what are the limits to sensing. This is going to be a completely different story on which we're trying to understand how we can use the key features of these machines to actually more easily prepare interesting states of matter. And the thing we're interested in is this phase called the chiral spin liquid. So I'll motivate quantum simulation very simply because I assume everyone here believes that it's a worthwhile thing to explore. And the reason is, as we think of like storing the wave function and studying it, we always have this issue that in a classical computer, it takes exponentially in the number of qubits to store and run our algorithm just from a storing of the wave function. But if you did have a quantum machine, the Hilbert space scales with the size of the machine, and the machine can time evolve just by letting it sit. So in principle, we could time evolve it for time t and time t. So there's this kind of like big win that in principle we get. The question that I think is fundamental is like, what are problems that we should solve? How do we build the machines? And how do we actually access the information that we care in these quantum simulators? The other question is, why spin liquids? So I kind of motivated quantum simulation. I should also motivate why we're interested in spin liquids. And the question is that it's a very important question because from multiple angles, but the way I like think about it is that there are examples of topological order. So there are physics that a phase of matter go beyond the Landau paradigm. And we know that they have a lot of interesting properties, in particular, the way that their quasi-particles can be used to kind of store and manipulate information. And if you've studied the surface code, that it's actually just the toric code in disguise. And people have also been looking at like more complicated topological phases in ion traps. Just wanted to flash that paper because of it. But the other side is that it's not only important, but it's also difficult. Like people have been looking for spin liquids in the solid state for 50 years now. But it's really challenging because the examples, for example, that we know how to solve in pen and paper, you actually have these very complicated interactions, for example, these four-body terms and plaquettes and stars. And so it's really hard to convince yourself that you actually have it and you have a material that can host them. But then even if you had them, it's super hard to actually get definitive measures that you can see them. In some sense, one of the features that you have these fractionalized excitations, the fractionalized excitations mean that you just see like broad spectra. And broad spectra can be from many things, including just disorder or junk. So it's really hard to kind of get a positive feature. So quantum simulators, in some sense, offer a new set of tools. And there's a wide variety of quantum simulators that have been showing up. And each of them has kind of different types of interaction, different capabilities, different kinds of controls, and new measurement schemes. And I think an interesting aspect is how do we leverage the new tools and the constraints and the opportunities of these platforms to build better schemes for seeing correlated physics. So the ingredients that I want to kind of use today, and these are motivated by these tweezer experiments that occur both in neutral atoms but also in molecules, is that I have long-range dipolar interactions. So I have flip-flop with 1 over r cubed on spin 1/2 particles. And the other element I need is that, and this gives me the frustration I need to build these liquid states. But on the other hand, I have this Kagame lattice that gives me a notion of geometric frustration. And this in principle is just one point in your phase diagram. So the one knob I'm going to think about is actually breathing. So what I mean by this is I take the Kagame lattice and I basically let the unit cells like spread out. And so at breathing equals 1, I have the Kagame lattice. That's the left side. And as I increase the breathing, the up triangles kind of move further and further apart. And this gives me kind of a family of models that I can study. And so the phase that I will be looking for is this chiral spin liquid. And so there's the spin liquid part, which means that it's a featureless state that has featureless spin correlation, but there's a notion of order at 0 temperature. And this is indeed the signature of this topological order. And the CSL has different features. The one I'll emphasize today for sake of time is this idea of these gapless edge modes that are topologically protected. And these are fundamentally non-local symmetry properties, whether it is by measuring the degeneracy, measuring modes on the edge, or measuring excitations. And on the other, and these are fractionalized excitation. On the other hand, we have this chirality, and this chirality comes from the idea of a time reversal symmetry breaking. So the fact that we have some handedness means that things are going to want to move in one direction rather than the other. And that tells us that if I reverse the arrow of time, I know if I'm going forward or backwards. In the case of our model, it turns out that time reversal takes our Hamiltonian to itself. That's why it's a symmetry. And takes spin to minus itself. But because I don't have spin order, it turns out that's not a good order parameter. So the thing I should look is this object, which I'll call chi, which is a chirality, which is nothing more than a 3-point correlation function across spins. So you should think about how non-planar spins want to be. And if they're non-planar, they kind of have a handness. They either have like a right hand or a left hand. And that is what signifies this time reversal symmetry breaking. And so we can try to look for this chirality because it is a symmetry breaking. In principle, it's easier. And if we take our model and we go to the very large breathing limit, these are the kind of ground states that we see. So what you find, and what I'm plotting is effectively the single site expectation value and the two site expectation value. What you see is this formation of this bond solid. So that is anything but a liquid by virtue of me calling it a solid. So that is kind of like a not very interesting phase. If I go all the way to the Kagame lattice, I actually have what seems to be a liquid. So if I look at the correlations on that particular lattice, I see that basically there's no features, there's no long-range order. Everything looks completely featureless. Turns out that this is a different spin liquid that's called as a Kagame spin liquid that I'll not discuss today. It's a different flavor. Ask me about it afterwards. But the interesting thing is, like much like the Goldilocks story, if you go somewhere in the middle, you get something that looks like the Kagame spin liquid in that it looks featureless when you look at the bonds. But now there's distinctive green. And distinctive green is exactly the measure of chirality. So if you look within a triangle, you can ask what's the chirality around that triangle. And you see that as you go from here to here, you actually break time reversal symmetry. And indeed, you have a different phase of matter than you had at the start. And this phase of matter is something that is that now has a gapped bulk. And hopefully, that's an easier phase of matter to study. In this case, it is spontaneous. But you can also prime it. If you're able to like add a chirality term, you kind of have helped the system move in this direction, and you still have the chiral spin liquid, but you no longer have it being spontaneously broken. Okay. Awesome. So this is kind of like the symmetry part. We can also ask about the spin liquid part. In principle, we can test for all of these properties, but let me show you kind of one of the starker ones, which is the emergence of these gapless edge modes. So one way that you can do this as a theorist, once you have these wave functions on a particular infinite geometry, is that you can actually cut the system in half. And what people have realized is that if you look at the reduced density matrix of that object, once you cut it in half, you actually have the features of the edge theory. So even though I just took an infinite cylinder, there's only bulk, I cut it in half, and somehow the system knows that if I were to cut it, there should be some remnants of an edge. And if you look at the properties of this spectrum and you plot it and you like do the right quantization, do the right quantum number matching, what you see is that the system picks up a chiral mode. So forget a little bit what the y-axis is. What you see is that there's this linear dispersion, and that linear dispersion goes with k. And this is exactly the feature of having a gapless linear propagating mode. And indeed, that's something that we get straight out of these wave functions. And moreover, we know that the properties of this edge mode actually match the theory that we expect out of a spin liquid, of this chiral spin liquid. So we can actually test the features of these gapless modes, and we can actually correlate them with the presence of this CSL. But this is, in some sense, theory land, right? All I've told you is how to find ground states and plot them with pretty pictures. The key thing is, like, can we prepare this in an experiment? Can we actually probe this in an experiment? And so the main question we were asking was exactly what happens if we try to prepare it. Is there a way to prepare it? Because we're trying to get a topologically ordered state in our quantum simulator, and we don't have access to a fridge that is able to cool it to 0 temperature. So the way that we want to think about this is if there is an adiabatic path, and if that path is kind of like gentle enough to allow us to prepare this phase. And what we find is that if you actually modify our Hamiltonian with kind of a local fields that kind of have this pattern on them, you can move from a paramagnet when this field is very large to the CSL state when this field is small. And this kind of gives us a path through a second order phase transition where in principle our preparations should scale only polynomial with the system size. Now, this is a feature that not only occurs in cylinders, but we can actually show that if we do the same calculations on a finite cluster, we have the same kind of features. The location of the phase is slightly different, but we believe that's a finite size effect. But in this tells us that we can prepare this using some sort of adiabatic ramp. Okay. Another question should be, okay, Francisco, maybe you've convinced me that you can prepare it. How do we see it? There's different experiments that we kind of propose, but one that I find the more stark is actually trying to see the dynamics of the edge mode. So what this corresponds to is if we think of our previous cluster, and we look at each unit cell and we look at the magnetization, initially, let's take that as a baseline. And we can ask what happens if I now rotate and do a spin flip on the edge, in which direction does the edge propagate? And what we see is that if, for example, if we flip this triangle over here, the blue excitation effectively tends to propagate to the right, and there's a wake of red on the back. And this is really hard to see on that plot. So a much easier way is to actually try to peel off the edge unit cells and plot the magnetization as a function of time, as a function of the distance of the spin. So what you see is that when we do the spin flip and we basically have a little bit of spin on the initial triangle, all the polarization only moves to the right, and we have this red wake coming in from the back. So this tells us that indeed we have a chiral edge mode. And the chiral edge mode actually doesn't care which triangle you start first. If we ask how much does the angle of this excitation is moved, whether we start on A, B, and C, we always see that it moves to the right. And if we flip the time reversal symmetry breaking state, we actually see that it just moves in the other chiral direction. So indeed, this is not just like some feature of like maybe the code or maybe something. We do have a way of controlling the chirality, of controlling the direction of this chiral mode by controlling the symmetry breaking of the state. And so what this tells us, and kind of like the reason why I like this project, kind of tells us that the unique constraints always offer new opportunities. And indeed, in these platforms, I think something that is very interesting is understanding how the particularities of these quantum simulators actually enable us to think of new ways to stabilize, new ways to prepare, and new ways of reading out whatever physics we want. And indeed, it kind of opens up questions not only in theory, but also in experiment. For example, what are other topological states that are easy to prepare? How do we get them? What are the paths? How do we study the excitations? How we further study the phase? How we characterize it? And how do we do it in an experimentally easy way? And how do we even like move past this and try to use, for example, non-unitary dynamics to kind of even speed up our preparation and our interrogation of this state? I think
questions for the second topic, and then maybe general questions at the end.
sounds good.
Yes, good. Yeah.
So why did you have to prepare the state adiabatically? Why can't you not just, cool it down and let it relax to the ground state?
So in these quantum simulators, you're basically, you've spent so much time isolating your atoms from the outside world that you don't have a way of like cooling them down generically. It's just like you now have an isolated quantum system. And the question is like, how do you kind of like steer it into the ground state in a way that's kind of robust? And the adiabatic protocol always gets us there. The question is like, how efficient does it do it?
Okay, I see. But you could also imagine wiggling stuff around. I mean, there's probably many ways of getting it to do what. I mean, it's probably not the only way, right?
Oh, yeah. We're not saying that this is the only way.
Okay.
This is the way that we know it works.
Mm-hmm.
In general, when you start wiggling, because these are strongly interacting systems, you usually just start pumping energy into your system or pumping entropy in your system. And then getting rid of that later, it's maybe even harder. So this kind of gives us a way of getting.
Wait, there was a question here.
What do you mean more specifically by non-unitary dynamics? Like, how is that helpful? And
the simplest answer is fridges work. And fridges work by coupling your system to something else. And then you can use it to extract entropy and reduce the energy. But that, if you were to just look at your system at hand, that's a non-unitary operation within the subsystem. So the question is like, how do we engineer baths, such that these ideas of it actually just cooling work. Because if we could do that in a robust way, we probably will be able to do this much more efficiently and effectively.
What was suggested before, right, of just like cooling it in the ground state, but
Yes.
with like certain help from outside.
Yeah, the question is, how do you design it? How do you what are the time scales? What are the ways that you need to do the coupling? How do you extract entropy? And a lot of those questions are kind of like, at least to me, are very unclear how to do it in a systematic and kind of like generic way. And maybe I think the other interesting question is, maybe you don't want to do it in a generic way. I have this state and I want to cool to this state. And then if I want to prepare a different state, I want to cool in a different way. And actually understanding what are the trade-offs, I think, is also an interesting theory question.
Good. We still have some time for questions. It could be for this topic or general. Maybe if you have a general outro, you can
Yeah,
go with that.
I'm gonna quickly, I don't know how to move them here, so I'm just gonna show some pictures. And if any of this seems interesting stuff, talk to me afterwards. But I think that the point that I wanted to kind of convey with these two examples and the third one is that this landscape, even though it feels like I kind of frame it as kind of sidestepping the quantum computing gap, I actually think it more broadly. I think this landscape is itself very interesting because it helps us to build technologies and build like application, build tools for doing science that kind of go beyond just necessarily digital quantum computation. And there's a lot to learn of actually how we take Schrodinger's equation and maybe even the idea of a qubit and actually interface it into ways that actually are useful for science and technology. And we need those concepts. We need the theory ideas, we need the proposals, we need the applications. And I think that these three directions kind of help us kind of map out this landscape much more effectively, and hopefully also serve as a stepping stone to a generic quantum computing technology. And indeed, a lot of it is needed to make quantum technology not only impactful, but also commonplace. And finally, a lot of it that I kind of tried to allude, and it would be also even more on the third case, is that indeed the constraints of the experiment and the theory it's kind of a flywheel. You need a communication to kind of like understand what are interesting questions that theories should ask. And in parallel, what the theorists can provide to the experimentalists in terms of like what are interesting experiments to run and what can we learn from them. And with that, let me thank you all for your attention and for the wonderful questions.
Great. If there's some final questions that could also be from online. So again, online, you're very encouraged to ask. Then please go ahead. Yes.
Thank you for your talk. I think I have a question still about the second topic because you prefaced it by saying that an important ingredient would be the tweezer arrays. It's just I kind of missed what about the tweezer arrays, like what properties of that system make it good so that I can prepare the chiral spin liquid?
The answer is that this tunable geometry. The fact that in these tweezer array setups, what they can do is they can define the location of the particles by some sort of like optical deflectors or kind of SLMs, and those allow you can in principle just tune in very many different things. So if you're not happy with your geometry on the first shot, on the second shot you can adjust it. So the fact of thinking of geometry as a tunable, continuous tunable parameter is kind of something that opens up these new design possibilities.
Great. Yes.
Can I ask a follow-up question on that? So let's say that you don't have like your spatial configuration of this chiral lattice, but you have something that nature has given you. Can you still incorporate it, you think, in somehow in your protocol that you can engineer the interactions to behave like such a lattice?
Yep. So in this case, it depends on the level of control that you have.
Mm-hmm.
If you have local control and you can Fourier engineer your way into a lot of places.
Mm-hmm.
If you have global control, it might be tougher to kind of control the relative strength of things. In this case, one thing I didn't emphasize because I didn't have time, but like one of the we believe that one of the reasons why this kind of moves us into these spin liquid states is that actually within a triangle there's a lot of frustration. And so the ground state really wants all the spin to be mixed between the three sites. And the moment you have like inhomogeneities there, it tends to kind of preferentiate a particular spin configuration. So how well you need to engineer that might affect how well you can do it.
Yeah.
Does that kind of answer the question?
Yes, but we can talk some more.
Okay.
Great. Anything online? No. Okay, then let's thank Francisco again. And as he said, you're welcome to come and talk to him about the topics.